I want to talk about an amazing new upgrade to RPM filters. For a long time, we've known that not all motor harmonic noise is the same. For example, biblades can produce 4 or more motor harmonics, whereas 5 and 6 bladed props typically used on cine-whoops show only 1 harmonic. Now, tri-blades are by far the most popular, and for these we usually see 3 bands or harmonics of motor noise, and that's in part why RPM filters are designed with 3 harmonics in mind. But the harmonics are rarely the same intensity. Usually there's a strong first, a weaker third, and often a nearly non-existent second harmonic. So to reduce filter delay, which we know is critical for great flight characteristics like low prop wash and smooth forward flight characteristics, some people have opted to select only 1 or 2 harmonic notches to be active at any time. But this didn't allow you to select which harmonics are active. It just allowed you to select the number. So in other words, you could select the first, or you could have the first and second on, or you could have all 3 on. But you couldn't choose, for example, 1 and 3, or 2 and 3, etc. Now, I've been asking for a long time, how valuable would it be if we could select any combination of RPM filter harmonics to be active? Well, Mr. Karate Brot, aka Jan Post, is a Betaflight developer who went a step further and designed each RPM filter harmonic to be on a dial, so to speak, from 0 to 100% attenuation strength. So this feature is called RPM filter weights, and it's new for Betaflight 4.5. It's not in the GUI yet, but it can be adjusted in the CLI. Now you can choose the attenuation strength of each harmonic, thereby allowing you to optimize RPM filters and by extension filter delay in extremely efficient ways. You might ask, well Brian, aren't RPM filters already really efficient and low in filter delay? Like, why do we need this? This is true for our typical mini quads, in part because the RPM of the motors is going to be relatively high, so the notches will generally be centered at higher frequencies, resulting in relatively low filter delay overall. Plus the fact that our mini quads are X4, so there's only 4 motors, and remember, the number of RPM notches that are generated is completely tied to the number of motors that you have. So you have 1 RPM notch per motor times the number of motor harmonics, which means 4 motors times 3 harmonics, that's 12 notches. And then of course you have 3 axes, so that's 36 notches in total. But where this feature really shines is on an X8 cine lifter or big motor rigs in general. Because on an X8 we have 8 motors, which means 8 notches times 3 harmonics times 3 axes, that's 72 notches. But also big motors tend to spin at a lower RPM in general than a 5-inch rig. So the notches will tend to be centered really low in the frequency spectrum, making for quite elevated filter delay. So I'm going to illustrate how this works and how various filter weights change the way motor noise is filtered, as well as how it affects filter delay. For this demonstration, I removed all other gyro filters. Low-pass filters are off, dynamic notches are off, and I'm only going to be using the RPM filters. Now, to ensure that bad things don't happen, I'm going to increase the filtering on the D term. But we're not interested in looking at D term, but we want to make sure that the drone doesn't freak out. So I'm going to have a PT3 on D term with a really low cutoff. This way, as I change the RPM filter weight, this will allow us to exactly see how the gyro and the filter delay associated with the gyro changes as the weights change from 0 to 25% to 50%, 75%, and 100%. So I used an automatic wobble script, which allowed me to perfectly replicate each line of sight test by having the copter automatically move to a specific pattern with just the click of a switch on my radio. This way, the average motor RPM is the same across tests. By the way, this auto wobble script is available on my Patreon if you're interested. It's also a really useful tool for doing typical basement tuning tests in a very confined area, so you can check that out if you like. So here are the results. Okay, so we're only plotting here the roll axis. So the red trace is the set point, that's the input from the sticks generated from the automated wobble controller, and the black trace behind it is the gyro, that's the copter's movement on roll. The lower panel shows the commanded motor down here and the actual RPM of each motor here above this, sitting at an average of about 10,000 RPM during the test. Next, we're going to look at the effect of the RPM filter weights on motor noise. So let's open the spectrogram and plot the pre and post filter gyro for the roll axis only in the test condition with the RPM weights at 0%. The thin line is the pre-filtered gyro and the thick line is post-filtered. That's after the RPM filters have filtered it. So we'll focus here on the first motor band because it's clearer to see. So here you can see the RPM filter weights are at 0%, so there is really no difference between the pre and the post-filtered gyro. But if we now compare the weights at 25%, we can begin to see some reduction in motor noise. At 50%, the motor noise is attenuated more, and 75%, the first motor band is almost gone, and then at 100%, it's completely gone. Now let's plot all the tests together to compare each step from 0 to 25, 50, 75, and 100% RPM filter attenuation, plotting the filtered gyro only. So you can see a nice systematic drop in each motor band. Let's focus now on just the third motor band. So notice that in the 50% filter weight condition, orange, the third motor band is already maximally attenuated. So technically using any greater filter weight here is probably unnecessary. The same is true for the second motor band. But remember, we're just referring to this specific drone. So next, let's examine the filter delay. So focusing on gyro delay, you can see that with filter weights at 0%, the gyro filter delay is 0.125 milliseconds, or 125 microseconds, which incidentally is one sample at 8K gyro rate. So presumably it takes one loop to compute post-filtered gyro, even if no filtering is applied. And then we can see a systematic increase in delay as we go from 25 to 100% RPM weights. So while these are modest changes in filter delay, you can see the value in tuning RPM filter weights to match the required level of attenuation, which as we know will be much more significant the bigger the drone. So now I'd like to talk about another practical application of this feature. There are some cases where it is essential to widen the RPM notches. That is, we sometimes have to lower the RPM filter Q to adequately attenuate the motor noise. And this, of course, is going to increase filter delay. For example, in some cases, the motor noise may not be very intense, but you might need a wider RPM notch to adequately filter it out. In this case, you could offset the extra filter delay as a result of widening the RPM notch, that is lowering the RPM Q factor, by then reducing the RPM filter weight. So in other words, making the notch wider with less attenuation versus typical narrower notch with the full attenuation. So I compared the delay with Q500 and a weight at 100% versus a Q of 250 with the weight at 50%. And as you can see in these results, the filter delay is approximately equal between the two. So it's a really nice way where you can really start to manipulate these RPM notches in ways that you could never do before. So let me know what you think in the comments, and don't forget to like and subscribe if you'd like to see more content like this.